Hi guys, welcome back to my YouTube channel. In the last video we designed some basic relays that are used for the power system protection. In this video we will design a complete protection scheme for the power system protection network in the SIMULINK. So as you can see that the basic electric power network is composed of generation, transmission line and distribution. Besides that we also have some transformers, step up transformer and step down transformer. So assume that we want to design a complete protection scheme for this transmission system. So assume that we are having a generator that can generate a power of 1 megawatt at a frequency 50 Hz. Then we have a step up transformer which is used to step up the voltage from 11 kV to 33 kV. After that we have a transmission line the length of which is 100 kilometer. So that's actually a medium transmission line. After transmission line we have a step down transformer that is used to step down the voltage from 33 kV to 11 kV. Finally we are having an RLC load whose rated power is 500 kilowatts. So let's go to SIMULINK to see the protection scheme of this power system. So this is my complete protection scheme for the current power system. As you can see that I am having a generator, two transformers, transmission line and then finally a load. So going towards the generation, so these are the parameters of the generator that is used in my protection scheme. After generator I am having a transformer, step up transformer. So these are the various parameters of step up transformer. So the low voltage winding is connected to 11 kV while the high voltage winding is connected to 33 kV. After that we are having a transmission line. So these are the parameters of transmission line. The frequency is 50 Hz and the length of the transmission line is 100 kilometers. After that moving towards the step down transformer. So these are the parameters of step down transformer. It is having a nominal power of 100 kVA and the high voltage winding is having a voltage of 33 kV while the low voltage winding is having a voltage of 11 kV. And finally we are having an RLC load. So the rated power of the load is 500 kilowatts and also the reactive, inductive and capacitive power is 50 watts each. So now let's simulate the system, but before simulating the system let's have a check on the relays. So I have used two differential relays in my current scheme. So this is the diagram of the differential relay. If you guys don't have the idea of designing the differential relay, so you guys can watch my last video to understand it completely. This is my second differential relay. Now before generating the fault, let's simulate the system in the OK condition. So I am simulating my system and let's see the voltage and current at the output of transformer number 1, which is my step up transformer. So this is my voltage. This is the 3-phase voltage at the output of transformer number 1. This is current at the output of transformer number 1. Now moving towards the transformer number 2. So the output of transformer number 2 is almost 1 into 10 to the power 4, which is almost 10,000 volts, which is basically the step down transformer, and the output current of the transformer number 2 is this one. So these are the normal voltages and currents just before generating the fault. Now let's introduce a fault at transformer number 1. So let's assume that I am generating fault at this transformer. Now let's simulate the system once again to see the output waveforms after generating the fault. So these are my voltage waveforms. You guys can see that at the instant when there is a fault, so the voltage is 0. As soon as the fault is recovered, so the voltage appears. But there is one more thing to notice, that after the fault is recovered, the initial voltage waveform is abrupt. This is because of the presence of inrush current in the transformer. So whenever the fault restores, so there is an inrush current, so there is a little fluctuation in the voltage waveforms. Now let's see the current waveforms. So these are my current waveforms after the fault has been occurred. Now let's restore the fault at transformer number 1 and generate a fault at transformer number 2. So let's generate a fault at transformer number 2. I am again simulating my system, and now I want to view my voltage waveforms at the output of transformer number 2. Now once again, at the secondary of transformer number 2, when there is a voltage, there is a dead voltage line, means there is no voltage. After the fault has been recovered, there are some fluctuations due to the presence of inrush current, and these are the voltage waveforms at the output of transformer number 2 after the occurrence of fault. Now let's restore the fault at transformer number 2 and simulate the system once again. Now the system will be restored to its original values. As you can see that this is the secondary of transformer number 1, and this is the secondary current of transformer number 1. These are the secondary voltage at the output of transformer number 1, and similarly the secondary current at the output of transformer number 2. So that's how you design the protection scheme for this power system. In the next video we will see some more protection schemes, so stay tuned for my upcoming videos. Allah Hafiz.